Hey everyone, welcome back to Chem Story. Today we're diving into an important steric effect in substituted cyclohexane, the 1,3-diaxial interaction. Ever wondered why bulky groups always seem to prefer the equatorial position in cyclohexane? Well, the answer lies in the 1,3-diaxial interaction. By the end of this lesson, you'll understand what 1,3-diaxial interactions are, why they happen, and how they affect the stability of a molecule. Let's get started. In a chair conformation of cyclohexane, each carbon has two substituent positions, axial and equatorial. Axial substituents point straight up or straight down, while equatorial substituents stick out more to the side. Now, when a bulky group ends up in an axial position, it runs into trouble. It creates steric hindrance with hydrogen atoms that are also in axial positions 3 carbons away. These steric clashes are called 1,3-diaxial interactions because they happen between an axial group on carbon 1 and axial hydrogens on carbons 3 and 5. This kind of clash increases strain energy, which makes the molecule less stable. The bigger the axial substituent, the stronger the repulsion, and the higher the strain. That's why bulky groups like tert-butyl, with its big CCH3,3 structure, strongly prefer the equatorial position, because that orientation avoids the axial clashes completely. To reduce steric hindrance, molecules naturally shift into conformations where bulky groups sit in the equatorial position whenever they can. Let's break this down with a diagram. In the side view, that's the leftmost image, you can see the chair conformation of methyl cyclohexane with the methyl group placed axially at carbon 1. Now the key thing to notice here is that axial substituents don't just sit there quietly. They interact with other axial hydrogens on carbons 3 and 5. These are the 1,3-diaxial interactions, and they create steric hindrance, which raises the strain energy in the molecule. Now let's switch to the top view. Here, it's even clearer. You can see how the axial methyl group at carbon 1 lines up directly with the axial hydrogens on carbons 3 and 5. And finally, in the rightmost image, we've got the electron density view. The overlapping yellow-shaded areas show the steric repulsion zones. They highlight where atoms are getting too close for comfort. These zones show exactly where the axial methyl group is clashing with the axial hydrogens, and that's what creates the steric hindrance. Altogether, this diagram makes it really easy to see how 1,3-diaxial interactions add strain to axial conformations. If the methyl group were placed in the equatorial position instead, those unfavorable 1,3-diaxial interactions would disappear, and the molecule would be a lot more stable. That's exactly why bulkier groups always prefer the equatorial position in chair conformations whenever they have the option. And here, in the rightmost image where we're looking at the electron density view, you can clearly see there's no steric clash at all between the substituent and the nearby hydrogen atoms. Everything's spaced out nicely, and the molecule is in a much more relaxed conformation. 1,3-diaxial interactions in cyclohexane and Gauche interactions in open-chain alkanes are actually caused by the same type of steric hindrance, and both increase molecular strain by about 3.8 kilojoules per mole per interaction. In open-chain alkanes, Gauche strain happens when two bulky groups are about 60 degrees apart in a staggered conformation. That close proximity creates repulsion. In cyclohexane, axial substituents experience 1,3-diaxial interactions with axial hydrogens on carbon 3 and carbon 5, and if you look at it using a Newman projection, those positions line up just like a Gauche interaction. So even though one happens in a ring and the other in a chain, they come from the same kind of steric clash, which is why they carry the same energy penalty, about 3.8 kilojoules per mole each. We can actually measure how much impact 1,3-diaxial interactions have by looking at the steric strain energy that different substituents feel when they're placed in the axial position. Just keep in mind, the strain energy values we're talking about here are based on the interaction between the axial substituent and just one hydrogen atom on carbon 3 or 5. So if you want the total strain energy, you simply double that number to account for both interactions. Take a methyl group, for example. When it's in the axial position, it experiences about 3.8 kilojoules per mole of strain due to steric clashes with axial hydrogens. Now, if we move up in size, an ethyl group feels about 4.0 kilojoules per mole, and isopropyl comes in around 4.6 kilojoules per mole, a little higher, but still in the same general range. But when it comes to tert-butyl, the strain jumps to 11.4 kilojoules per mole, and that's a big leap. The reason is simple. Tert-butyl is just too bulky. Its 3 methyl branches create serious steric clashes when they try to squeeze into the axial position. With smaller alkyl groups, most of the strain comes from hydrogen-hydrogen repulsion, but for tert-butyl, those large methyl arms end up in direct conflict with axial hydrogens, and that ramps up the strain dramatically. So much, in fact, that the axial conformation basically doesn't exist when tert-butyl is involved. That's why tert-butyl groups almost always sit in the equatorial position, because that's where steric hindrance is minimized. Interestingly, halogens like chlorine and bromine actually have pretty low 1,3 diaxial strain values, around 1.0 kilojoules per mole. And that might seem surprising at first, because halogens are pretty big atoms. But here's the thing. Their carbon-halogen bonds are longer than typical C-C or CH bonds, so the halogen atoms end up sitting farther away from the axial hydrogens. That extra distance helps reduce steric repulsion, which is why their 1,3 diaxial strain is much lower than you'd expect just based on their size. Another interesting case is the cyano group, which has an extremely low 1,3 diaxial strain value, just 0.4 kilojoules per mole. That's because the cyano group is sp hybridized, which means it's linear in shape, and because of that, it barely gets close enough to interact with nearby axial hydrogens, so there's almost no steric strain at all. This shows us something important. Steric strain isn't just about atomic size. It also depends on things like bond length and geometry. So understanding 1,3 diaxial interactions is super helpful when predicting the stability of substituted cyclohexanes, and it plays a key role in conformational analysis overall. Thanks for watching, and I'll see you in the next video.